Welcome to the third and last video of week 6 of this introductory course on synchrotrons and X-ray free electron lasers. Now this video is concerned first with the complementary scattering methods of X-ray reflectivity and the more general technique of small angle X-ray scattering. Finally, we will provide some insights into experimental approaches unique to diffraction and scattering experiments using X-FEL radiation. X-ray reflectivity does exactly what it says on the can. One measures the specular reflectivity of X-rays as a function of incident angle. The range of angles typically lies between a little below the critical angle for total external reflection and a few degrees. From this data, diverse information can be extracted, including the electron density profile down to the penetration depth of the sample, surface roughness, and, in the case of layered systems, the interface roughness, layer thickness, and layer density as well. Also, the properties of multilayer structures can be investigated, and even real-time kinetics experiments monitoring film growth down to picometers per second growth rates, or even slower than that. The reflectivity amplitude, remember we actually measure the intensity proportional to the square of the amplitude, this amplitude is given by the Fresnel equations for reflectivity and transmission, and is equal to the difference in incident and transmitted angles across the surface divided by their sum, as shown here. Exactly at the critical angle, therefore, alpha prime is equal to 0, and the reflectivity is unity, as we would expect. We should also recognize that the reflectivity will drop off thereafter very rapidly with the incident angle, as the difference in angle between the incident and transmitted beams rapidly becomes very small indeed. From this, it can be easily demonstrated, using the relationship between delta and alpha, that the reflectivity intensity, big R, which is the square of little r, is equal to the expression shown here top left. For angles significantly larger than alpha c, this is accurately approximated by big R is equal to alpha c upon 2 alpha, all to the 4th power. As shown here with this double logarithmic plot and a gradient of -4. Because alpha is proportional to the scattering vector q, the reflectivity curves therefore drop off with the inverse 4th power of q. Note also that because the electron density of material in electrons per cubic angstrom oscillates around approximately Z upon 25, where Z is the atomic number, a very rough and ready rule of thumb emerges that the critical angle in degrees is equal to the square root of the average atomic number divided by 30, multiplied by the wavelength in angstroms. The reflectivity drops off even more rapidly if the X-rays are being reflected off a rough surface, even for roughnesses of the order of a few angstroms. Now, if we describe the average roughness actually as a Gaussian distribution with a roughness standard deviation sigma, the reflectivity above the critical angle drops off as the perfectly flat surface would, but now multiplied by the Fourier transform of the roughness function, that is, the exponent of -2k alpha sigma all squared. For the more maths adept student, it's briefly mentioned that this can be explained by the convolution theorem. The surface is simply the convolution of a flat surface with the Gaussian roughness function, and therefore the scattering pattern is the Fourier transform of this convolution. In other words, the reflectivity curve of the perfectly flat surface multiplied by the Fourier transform of the roughness function. The example on the right shows the reflectivity of silicon for 10 kiloelectron volt photons as a function of angle and surface roughness. Thin films grown on materials have many applications, such as, for example, in the heteroepitaxial growth of electronic devices, for tribological coatings, protective layers, and in lipid biology, to name just a couple of examples. A characterization of these layers is therefore of high technological importance. The condition for constructive interference is, as always, that the optical path difference, shown here as a solid red line, must be equal to an integer number of wavelengths. This is essentially just a restatement of Bragg's law, where alpha is equal to theta, and we approximate sine alpha with simply just alpha, as long as we express that in radians, for the shallow angles relevant to X-ray reflectivity. The d spacing is simply the film thickness delta. Now this causes the reflectivity curve to exhibit oscillations known as Kiesig fringes. The separation between fringes is simply lambda divided by 2 delta, though the fringes actually deviate from this in the first few oscillations due to dynamical effects not covered in this course. The film thickness can thus be directly obtained from the Kiesig fringe period. On the right, the reflectivity curves for 10 nanometer films, the first element, on atomically smooth substrates, the second element, are shown. Note that the phase of the Kiesig fringe oscillations differ by approximately pi for gold on silicon compared to silicon on gold. This is because, in the latter case, the reflection at the interface between the film and substrate undergoes a pi phase shift when the film is less dense than the substrate, while when the film is denser than the substrate, no such phase shifts occur. A simple illustrative example is shown here. A quasi-crystalline alloy of titanium nickel zirconium was grown on an atomically flat sapphire substrate to a thickness of approximately 120 nanometers. This was then measured some days later, and in the intervening time, the film had been exposed to air at room temperature and pressure. The rapid Kiesig oscillations associated with the film itself agreed very well with the film thickness of 120 nanometers, but these were further modulated by a much slower oscillation, and this was associated with the upper 4 nanometers of the film being oxidized during its exposure to air, thereby giving it a different electron density, producing this slow oscillation. The decrease in reflectivity with surface roughness can be exploited in situ X-ray reflectivity experiments in order to monitor film growth. If the film grows in a monolayer for monolayer manner, this is called Frank van der Merwe growth, then the roughness will vary sinusoidally, being maximally rough when each new monolayer is half complete. So by monitoring the reflectivity during growth, the growth can be followed monolayer for monolayer. In addition, if the material is crystalline, a good angle to choose to monitor the growth is about halfway in between the direct beam, i.e. at 0 degrees, and the first Bragg peak in the specular direction. So this might be the 001 Bragg peak if it's not a systematic absence. Here, the reflectivity is at a minimum because it's between the maximum of the direct beam and the maximum of the first Bragg peak. But also it varies most strongly with roughness, relatively speaking. Because of the weakness of the signal, the use of synchrotron radiation is therefore quite important. Indeed, note that in the curve on the right, every second roughness oscillation seems to be stronger. This is due to the Kiesig fringes passing through the point of observation as the film grows. The movie of the growth in real time is shown here as an example. Note first that the intensity initially increases at the start of growth, which is indicative that the substrate material on which the film grew was not perfectly atomically flat to begin with, and that the first part of the growth filled in this incomplete monolayer. Also note that with increasing film thickness, the oscillation amplitude wanes. This is due to the fact that growth is not perfectly layer for layer, and that with time, the film accumulates an underlying roughness. This is called Stransky-Krastanov growth. X-ray reflectivity is in fact just a special form of small angle X-ray scattering. We discuss this technique now. X-ray scattering from larger objects up to about a micron in size can also provide important structural and dimensional information. Consider an object with a characteristic length d. The ratio of this length to that of the X-ray wavelength being used can, depending on the system, be anything from about 20 to several thousands. Scattering is thus typically over angles lambda upon d, which can thus be anything from a couple of thousandths of a degree to a couple of degrees. Importantly, the samples investigated using SACS needn't be crystalline, and the large majority of experiments are on non-crystalline samples. Scattering occurs, just as it does in X-ray reflectivity, through electron density variations delta rho, and not from individual atoms, the case in diffraction. Typical information extracted from SACS include characteristic shapes and sizes, surface area to volume ratios, and, in special cases, the relationship between two well-defined sizes, such as between the radius and the thickness of a circular platelet. Just as the scattering intensity in diffraction scales with the square of z, the atomic number, SACS signal increases with the square of delta rho. In general, one assumes the individual scatterers in an ensemble of these investigated with SACS are well separated. By well separated, it's meant that the neighbor-to-neighbor distances are significantly larger than the coherence length of the radiation being used. In this case, each particle can be regarded as a separate entity, in which case the scattering intensity increases linearly with NP, the number of illuminated scatterers. SACS has many applications, for example, as an adjunct to protein crystallography, in order to determine the overall shape of a given protein structure. Also, it's used in cell biology, colloidal and polymer sciences, in nanostructures grown either naturally or specially fabricated on thin films, to name just a few disciplines. We have already determined that scattering angles are measured in small fractions of a degree, up to 1 or 2 degrees. Hence, it should not come as a surprise that the ratio of the distance between the sample and the detector recording the SACS signal and the detector linear dimensions is large. Now, the sample to detector distance is typically measured at SACS beamlines in a few meters. It's important to avoid spurious signal arising from other elements at the beamline, such as forward scattering from X-ray windows or indeed air. So, for example, the path between the sample and the detector is normally evacuated using a long flight tube as shown here, while the entrance window to that flight tube is typically fabricated not from amorphous material such as Kapton, which would produce its own Sachs signal, but from thin sheets of highly crystalline material, such as diamond or mica. Scattering from cleanup slits upstream of the sample must also be suppressed. Just as in normal crystallography, the scattering vector Q connects the direct beam with the scattered beam, and, as before, is equal to 2k sine theta, or here just simply 2k theta because theta is such a small number, so long as theta is expressed in radians, by the way. The Sachs signal tends to be circularly symmetric as a large number of randomly oriented particles are probed simultaneously. It's therefore the radial signal that is of interest. Now there are three regimes in Sachs. The small q regime, for which q is much smaller than 2 pi upon d, where d is the characteristic scale of the object being investigated. Then there's the regions where q is larger than 2 pi upon d, and there is an intermediate regime. Now, the intermediate regime can provide information on fractal scaling in systems with nested characteristic scale lengths, and we will not go into details of this region here. The low Q regime is known as the Guinea regime. Because the length scales probed here are generally much larger than the characteristic length d, all details of the particle shape are completely lost. Instead, one obtains only information in the Guinea regime on the overall size, or more accurately, the so-called radius of gyration, Rg. Now, this radius of gyration is actually equal to the radius of inertia in classical mechanics, and is the radius of a spherical shell of 0 shell thickness, but having the same mass, or more accurately here, the same scattering power as the object under investigation. Guinea's law states that, at low Q, the intensity follows the form of IQ is equal to I0 multiplied the exponent of minus Q squared Rg squared upon 3, and is valid for all objects, as long as A is much larger than D. A plot of the natural logarithm of IQ as a function of Q squared therefore results in a gradient of minus Rg upon 3 in the Guinea regime. The Porrod regime describes the other end of the scale at large Q, where length scales much smaller than the object are being probed. Now, if this is small enough, the X-rays will see the object as being smooth on this scale, as within this small yellow circle shown here. As scattering occurs where there is a change in electron density, this regime is actually equivalent to that of reflectivity, and the intensity should fall off as 1 upon q to the 4th, as we argued earlier in this video. A plot of IQ versus 1 upon q to the 4th should thus produce a straight line with a gradient equal to 2 pi a, where a is the sample surface area. This regime is hardest to probe due to the associated low intensities. We finished this week with a brief overview of diffraction and scattering experiments at X-FELS. As early as 2000, it was predicted that crystallites could survive irradiation by X-FELS just long enough before exploding, and this was experimentally confirmed in 2011 for nanocrystals of photosystem 1, recorded at the LCLS in Stanford, California. This concept of diffraction before destruction led to the method of serial femtosecond crystallography, in which successive diffraction images of freshly delivered and randomly oriented crystals are recorded. The delivery method may be through some sort of liquid jet, as just shown here, or an aerosol, or on a fixed membrane system. Each method has its relative advantages and disadvantages. So, for example, liquid jets are prone to freezing as they expand into vacuum, plus only a very small fraction of the crystallites are ever irradiated. The jet moves at a few meters per second, And this means that at the LCLS, which runs at 120 Hz, the jet moves forward by approximately 5 or 6 centimeters in between X-FEL pulses, a stretch of material which can contain several thousand or even some tens of thousands of crystals. This method is therefore highly wasteful. Increasing the repetition rate helps only so far, as the jet itself is ripped apart by the X-FEL and requires some time to heal itself and flow continuously once more. On the other hand, narrow liquid jets have a relatively low background caused by the water or other solvents the crystallites happen to be traveling in. Because the crystal orientation is random, each pattern must be ascertained individually, and sophisticated programs have been developed to perform this automatically. As we shall see in the next slide, this is exacerbated by other factors associated with the X-FEL pulses. In order to obtain a complete diffraction pattern with a resolution that allows identification of individual atoms, several 100,000 or even more partial patterns must be recorded. So, what are the motivations for performing macromolecular crystallography at X-FELs? And what obstacles, other than sample delivery, stand in the way? First, because the crystals anyway explode immediately after irradiation, cryocooling becomes entirely redundant, and the increased mosaicity of protein crystals caused by cryocooling can therefore be completely bypassed. Also, because the X-FEL pulses can be routinely focused down to submicron dimensions, very small crystal sizes excluded to synchrotron radiation experiments can be used, which opens up access to new systems which have resisted crystal growth to dimensions of the order of a few microns or larger to date. A large class of proteins, called membrane proteins, is a premier example of this. Also, if one assumes a given density of crystallographic defects per unit volume in a crystal, smaller crystals will be crystallographically purer. Perhaps most importantly, X-FELs allow one to follow chemical dynamics on a sub-picosecond timescale, even down to a few femtoseconds in principle, which is highly relevant for many biochemical processes. Biology is all about change, the response to internal and external physicochemical stimuli, which is excluded to more conventional synchrotron studies of cryocooled systems. It's only X-FELs which can provide this avenue of research. Accurate data interpretation is hampered by many issues, however. First, there are large fluctuations in the energy of individual pulses, which can vary by several tens of %, although this particular aspect is slowly improving. Secondly, the central energy of any single X-FEL pulse may fluctuate by a few tens of electron volts due to the random nature of the Sayce process that produce the pulses in X-FELs. This means that the shell of the Ewald sphere increases in thickness with Q, varying approximately a sine squared theta between 0 in the forward direction and 2 delta K in the backward scattering direction, whereby delta K is the difference in the minimum and maximum wave vectors associated with the energy difference. Because each diffraction pattern is recorded over a few femtoseconds, there's no possibility to rotate the crystal during exposure. This means that diffraction spots are likely to represent only a partial integration over the entire diffraction Bragg peak. This is most obvious in the forward scattering direction, where the Ewald sphere is still very thin, and less so as Q increases, though these peaks do become increasingly weak. Lastly, the size of the crystallite responsible for any given diffraction pattern is completely unknown. Is the signal strong because the crystallite was large, the X-FEL pulse energy large, or due to a coincidental alignment of the Ewald sphere with the diffraction pattern in reciprocal space? Actually, this randomness in crystal size can be turned to advantage. After many shots numbering the hundreds of thousands, Each diffraction peak will have been partially sampled many times at different positions relative to the eval sphere and originating from many different crystal sizes. The crystal can thus be modelled as having a kind of Gaussian cloud form, representing an average of all the crystallite sizes and orientations. Single particle imaging using X-FEL radiation was one of the first long-term goals when funding for X-FELs was being sought. Single particle imaging is the coherent cousin to SACS. The whole mesoscopically sized particle is irradiated coherently and the scattered pattern is recorded. This is essentially the same as coherent diffractive X-ray imaging, the major difference here being that each particle is completely obliterated after every shot. X-FELs have 100% transverse coherence, making it possible to record the coherent scattering pattern or speckle of substantially sized objects, in particular non-crystalline objects. The Fourier transform of that speckle, assuming one can solve the phase problem, should provide a 2D slice of the object associated with its orientation relative to the eval sphere. A complete reconstruction of the whole three-dimensional structure requires that all orientations have been sampled to a sufficiently high angular accuracy. The problem with non-periodic objects is that they have no Bragg peaks with which to index them and through this determine their orientation. In order to overcome this, sophisticated iterative algorithms have been developed based on the EMS or expand, maximize and compress paradigm, explained in detail in the references below. Single particle imaging is also fraught with technical and experimental obstacles. First, the sample holder can potentially add spurious signal to the already weak signal from the actual sample. In addition, it's important that any forward scattering of cleanup slits or other optical elements is entirely avoided. Lastly, it's important that sample-to-sample reproducibility is high. If a significant fraction of the samples have a different architecture on the scale to which the object is to be resolved, the reconstructed model will contain features of both. With this, we finish our discussion of scattering and diffraction experiments at synchrotrons and X-FELs. X-ray, reflectivity, and SACS offer complementary methods to crystallography methods, not least in the field of non-crystalline and mesoscopic objects. Scattering experiments at X-FELs promise a bright future, especially in those studies of dynamics of systems such as conformational changes in proteins under in vivo-like conditions. X-FEL science is still in its infancy. The unprecedented jump in peak flux associated with the X-FELs has opened up new avenues of as yet unexplored fields of protein research and into their structure. And we can be confident that great new science will emerge as a consequence of this. Next week, we turn our attention to spectroscopy experiments at synchrotrons and X-FELs.